spite of political and security obstacles, we have Landau lectures interrupted. Also today some technical small problems. Now, Landau lectures are sponsored by our Landau Center in Analysis and Related Areas, which is named, as you know, after Edmund Landau, who was the first mathematics professor in Müller University and was involved in Göttingen Mathematical School. And I want to mention that the first Landau lecture was given by Professor Jürgen Moser, who unfortunately passed away. This was in October 1991, and since then we have 11 Landau lecture series, and today we have 12 Landau lecture series, and this will be the first one in applied mathematics. It will be given by Professor Stefan Müller, who is a co-director of Max-Planck Institute in mathematics for science. This is a kind of new creation, not as Max Planck Institute in Bonn, but this is a new lens of. And Professor Müller was invited speaker in Berlin's 98 ICM Congress, and he received also several mathematical research and mathematical awards. And I hope we'll enjoy these lectures, and I want to stress that all lectures are independent, but everybody are welcome for each one. And there will be a kind of colloquium style, and so I hope you'll understand everything. And as we want to develop here applied mathematics area, this will be a kind of help for us.
Thank you very much. It's a great honor to have been invited to give the Landau lectures, and I'm very pleased to be here. And I would like to thank you all for the invitation, in particular Professor Kiefer and Reimer Sternheim for preparing my visit so perfectly. So, as you have seen, the titles of the individual lectures, they look very different, but there is, and they're on different subjects, but there is an overall theme which connects them. And if I had to say it in one word, it would be microstructures. So what are microstructures? That's a notion which originates in material science, or if you like, in engineering. And there it refers to any kind of structure which is between the atomic scale. It's larger than the atomic scale, but much smaller than the scale on which we make normally observation, or on which an engineering specimen would be operated. So it could be fine inclusions in a material, it could be a microstructure of different phases, it could be complicated mixtures of materials, it could be the fine structure of scales of a fish, which reduces the effective friction on the surface. There are many things like this. And in fact, if one would say it in a very drastic way, material science is to a large extent the science of engineering the microstructure in such a way that you get a desirable feature of the material. And so, for example, even if you take a very standard material like steel, it may look to you like a homogeneous material, but the fact that you have so many steels and you have sort of properties which are tunable from sort of very tough but also brittle to sort of soft but very ductile, has to do exactly with engineering the microstructure, sort of very complicated mechanical and heat treatments. And so while traditionally sort of this has been done sort of on the basis of a huge experiments, trial and error if you like, and sort of building some intuitive understanding of the material, sort of a more modern complementary approach is to also try to make models and simulations. And so this, the role of this microstructure is even stronger in what they call advanced or sometimes smart materials, which try to sort of adapt to their environment, and again they do that usually by changing their microstructure, which give them unusual property. So I've brought some examples sort of which we study in our group here, and you can sort of look a bit at them while I talk on. So on the mathematical side, microstructures maybe not such a clearly defined notion, but sort of following the lead of Tatar's work in the late 70s, I would say microstructures are oscillations and concentration effects. Thank you. Oscillation and concentration effects in nonlinear partial differential equations. You want to study those oscillations which are compatible with the PDE. And if you study a case where there's no intrinsic length scale, like standard elasticity, typically the structures will be infinitesimally fine, and then you have to sort of invent new mathematical objects like the Young measure to capture them. If the problem has an intrinsic scale, then of course they're cut at some certain scale, they're not infinitesimally fine, but then you're interested in sort of how the small parameter influences the problem in the sense of a singular perturbation. And so a singular perturbation is also what I want to discuss in the first lecture. So here there's a very short overview of the three lectures and their connection to the general theme. So today I want to talk about a very classical but unsolved until recently problem in elasticity, namely how you pass from three-dimensional nonlinear elasticity, where we have a model which is essentially defined by just assuming the basic invariances you want to have, and then we agree what the functional is, what the structure of the function is, to lower dimensional theories. For example, a theory for a two-dimensional object like this sheet of paper. Of course, I could treat it fully three-dimensional, but I mean, A, this would be not very efficient. B, I may get structurally new insight if I use that this is only a two-dimensional object. And by contrast, this lower dimensional theorem, there are many, many theories, and they're usually derived by making some clever assumption what the solution of the 3D problem should look like. So then you have a few free parameters, and then you get a two-dimensional problem which sort of determines the parameters, so to speak. But conceptually, what you would like is not to make any assumption on the solution, that the problem itself decide what it wants to do, but pass to a limit where the object becomes thinner and thinner, and then there should be a rigorous way to get the limiting theory. So that's what I want to talk about today, and that's sort of a classical example of the singular perturbation. The small parameter is the thickness, and actually you see you pass from a second-order PDE to a fourth-order PDE as this parameter goes to 0. Then the second lecture will be about magnetic microstructure, and if I want to explain it in mathematical terms, it's essentially a perturbation of the harmonic map problem by a non-local term. And although this non-local term is naively seen lower order, it crucially influences actually behavior on the scales you're interested in. And the last lecture will come back to this microstructure in crystals, and the general theme will be relation between non-convexity of the energy functional and sort of fine-scale oscillations. And there actually I will mostly focus on the analytical aspects and not so much on the modeling aspects, and in some sense there has been, if you like, a transfer from applied mass from the study of these microstructures into pure mass because of using things we had learned from studying these microstructures. There's now some sort of new example regarding sort of Hilbert's 19th problems on the regularity of variational problem, but you can hear that story in the last lecture. So today I want to speak about this dimension reduction in elasticity, and I would like to dedicate this lecture to the memory of Fritz John, who for all of us working in elasticity and in fact in analysis was a great inspiration, and who, like Landau, was driven out of Göttingen by the Nazis. Can we switch this off? No? Yeah, okay. So it was in fact a discovery, a point of view of Fritz John, that really the problem of reducing from 3 dimensions to 2 dimensions in elasticity is mostly a problem of geometry. It's not so much a problem of the kind of elastic constitutive behavior, but it's essentially a problem of geometry, and you can all try this with a sheet of paper. If you take a rigid elastic body, then it's clear you can rotate it freely in space. So rotation costs no energy. Now what you see, so therefore, and this sheet of paper obviously requires only very little energy to be deformed. And how does it do that? Well, if you try it for yourself, you see essentially locally what you do is you only perform a rotation. And now you achieve a globally non-trivial deformation because this rotation changes from point to point. And that's exactly what you have to understand. And when you take this point of view, already you're not so surprised that curvature will eventually come into the problem, because curvature exactly measures how the normal changes, or in other words, how the rotation changes. So to get started, let me start with a purely geometric statement, which is at the core of the later analysis. So all this is joint work with Richard James from the University of Minnesota and Gero Frieseke, who was at Oxford and who is now at Warwick. So we first want to work in 3 dimensions. In fact, we can work in n dimensions. So U will be a bounded domain in Rn, and for the expert, I should say that the boundary regularity we need, for example, Lipschitz would be sufficient. You could probably even do a little bit more, but Lipschitz will be enough for our purposes anyhow. And V will be a map from U into Rn. And here is the theorem. So if you like, there exists a constant which depends only on the domain, such that for all maps V, and if you like everything to be well defined, you should require that they're in the Sobolev space W12. This means nothing that the gradient is still square integrable. There exists a rotation, so a single matrix R in SON, such that the following estimate is true, namely the distance of the gradient, the L2 distance of the gradient from this fixed matrix is bounded by a constant times the L2 distance from the set of all rotations. Maybe So you see, this clearly must use the fact that we're dealing with a gradient, because if we had an arbitrary matrix valued function, that could obviously not be true. And so to gain maybe some understanding what this means, let's consider some special cases, so let's make some remarks.
So what is here is the distance between the gradient?
It's a sort of, okay, if you like to write it out, you, at each point, this is a matrix, and this is a set, so you can talk about the Euclidean distance, say, of a point from a set, and then you integrate. So here is the distance from a single matrix.
So let's say that the right-hand side is 0. So it's
Yeah, that's exactly what I wanted to say now. So the first example is, let's assume that the right-hand side is 0. So that simply means that at every, or if you like, at almost every point, the gradient is a rotation. And then what the theorem says is, in a domain, so in a connected set, the gradient is actually constant. So that's actually a very classical theorem.
This is a rigidity type?
That's a rigidity type theorem, and that's sort of classical in the geometry and also in continuum mechanics. It's relatively easy to prove if the map is C1, because then you get that it's locally invertible, and then, so if you have a map which is C1, then you get that it's locally invertible, and if you work a bit more, you can show that it's really an isometry not only for the differential, but that it's a real isometry. It's a map which preserves length, and from this, it's a nice exercise to show that such a map must be linear. In fact, that argument even works in Hilbert spaces. So the statement is actually true if you only assume that the map is Lipschitz and that it has a differential almost everywhere. For this you have to work a bit harder. So this is a rigidity result, and if you like, our theorem is the optimal quantitative version. Namely, it says that the distance from a constant is in a linear way bounded by the distance from the set. And the fact that this bound scales linearly will be crucial to apply it to plates, because then you have to apply it to little cubes of the size of the thickness and to sum up. And if you had another power here, then the theorem would be easier to prove, but then it wouldn't apply. So the second remark is that Fritz John actually proved that theorem under a stronger assumption, namely that you have a quasi-isometry, so that you know, at least locally, let me just put locally. And then he first shows that you can extend this globally by a very intricate geometric construction, sort of using confocal ellipses, and it's a very nice, it's kind of a modification of this proof where you use intersecting circles. And then he finally arrived at this theorem, and in fact, it was this result of Fritz John which was the birth of BMO, the space of functions of bounded mean oscillation, and you can see sort of why this would come here. The natural scale invariant version of this theorem is to divide by the volume of U, and if you have such an assumption, you have a global bound on this, and then you naturally end in BMO. In fact, I should say there's also an LP version of this for all p strictly between 1 and infinity, and the L infinity version exactly gives you only, of course, BMO on the left-hand side. If you put L infinity on the right-hand side, and there's a logarithmic spiral which was known to Fritz John, which shows that this is optimal. So the third remark is that Bob Cohn, who in his PhD thesis sort of worked gave a new proof of Fritz John's result. What he could prove is again the optimal estimate, but not for the gradient, but only for the map itself. So what he could prove is some kind of Sobolev version where you put the distance, let me be a bit short here, where you put the distance on the right-hand side and you get something about the map on the left-hand side, but his proof doesn't work for the gradient. So another connection.
On the right-hand side you have gradient, or?
Yeah, on the right-hand side you have the gradient, yeah, sorry. So this, of course, would follow from this from the Sobolev embedding theorem, and but he could only prove this version. Another connection is with Reshetniak's work on quasi-regular or quasi-conformal maps. So what he showed is essentially the compactness version of this result, namely that when the right-hand side goes to 0, the left-hand side has to go to 0 as well. And so what he proved is, on the one hand, it's more general because he works not only with SON, but he works with all conformal matrices. So, and he assumed that this goes to 0 in Ln, and that the gradient, so let's do this for a sequence now, that the gradient converges weakly to some limit in Ln. So then this implies that the gradient converges strongly to some V in Ln, and then that in turn implies that this is conformal and therefore must be a Möbius map in 3 or more dimensions, or conformal in 2 dimensions. So it's on the one hand more general because he allows an even more general set here, but on the other hand he doesn't get any quantitative comparison of the right hand side and the left hand side. And the last remark, which connects it to another classical theorem, if you linearize this, then what do you get? Well, if you linearize, say, at the identity, then the distance from SON becomes simply the symmetric part, because the skew matrices are the tangent space to SON. And here you get the full gradient still, when you linearize, because you look at the distance from a single matrix. So what it says that you can control the full gradient up to a constant by its symmetric part. And that's the famous Korn inequality, which is the workhorse of linear elasticity. So if you like, if you're an elastician, you would view this as a nonlinear Korn inequality. If you're more a geometric person, you would see it as a quantitative version of this rigidity estimate.
So again, what happened when you take here the...
Okay, so what you get is, so I just do it formally, so gradient V would be the identity plus epsilon times gradient U, and R would be the identity plus epsilon skew plus higher order terms. So W is Q. And then the assertion is that the integral of the gradient of U minus the skew matrix is controlled by a constant and the symmetric part. And that's the crucial equality in linearized elasticity, because in linearized elasticity, the gradient never shows up alone. The only thing which shows up is the symmetrized part, because you need infinitesimal rotational invariance, which means exactly invariance under adding skew-symmetric matrices.
Can you say something about how C of U depends on the geometry of U?
So I will say something later how it depends on the geometry when you go to very thin domains, because that's exactly what we'll need for the study of plates. And so now that you're asking is, say, if you take a fixed cross-section and you take, say, omega h of this form, then the constant will behave like h squared. Well, okay, then let's see. So we did this for 3 dimensions, but since it essentially comes from this covering argument, it should be true in any dimension. So this would then be a set in Rn minus 1. So, and that essentially comes from, I should check, but it's not difficult to check. This essentially comes from covering this thing with cubes. But we will see it at least in the special case of 3 dimensions and a 2-dimensional surface later in the talk. Otherwise, so, okay, you could do something similar, say, for domains which become small in 2 dimensions, or something which are of the form S cross something which strings. Then I think you could say certain things. Generally, I mean, I don't know. For example, I don't know whether it's optimal for the sphere if you say among sets of equal volume. That one would have to see.
Volume, for example?
Sorry?
If U is convex, can you balance in terms of the volume of U?
Okay, I haven't. Well, I mean, no, because I think it's in some sense if you have one small direction that makes a constant small. I think that's pretty clear. So if you would need some kind of, I mean, you could probably bound it by sort of a ball inscribed and sort of a ball outside or something like that if you want the uniform bound. But I mean, you can see it in elasticity. If the thing is sort of thin in certain directions, then it's easy, then it becomes almost possible to beat this. Because you say you can take 2 sub-pieces, which you bend whichever way you want, and then you just need sort of a boundary layer to glue them together. So in fact, for example, I don't know whether this constant is attained. Because it's not like it's a nonlinear eigenvalue problem, but both sides are equally strong. So there's not an easy compactness argument which would say that it's attained. And I don't know whether it's sort of maximized, for example, for the sphere among sets of equal volume. This would all be interesting questions. Okay, so that's the geometric inequality I will use. And so now what is the relation between 3D and 2D elasticity? So what we want to look at is a cross-section which is a 2-dimensional domain, say again with Lipschitz boundary, and which has height h. So that's our domain omega h, which is S cross minus h over 2, and we want to, say, look at maps U, which map this into another set, into 3-dimensional sets. So now I put n equals 3 because that's the most interesting case. And we're interested in the limit as h goes to 0. Now it's a bit difficult to study problems which are defined on different domains. So what we do here is we rescale to a domain of unit height. And we call that omega. And we call the corresponding map here, we call y. Why not? So then if you want it in formulas, Z2, Z3, V of is Y of Z1, Z2, and H times Z3, over H, and therefore the gradient of V is, if I write it out, the first two partials are the same, and the last one, of course, picks up a 1 over H, and this I will call, gradient prime for the in-plane gradient, and the whole thing I will simply write gradient H of Y. This simply captures the fact that I've rescaled the third variable. And then with this goes some elastic energy. And I write it directly, I directly normalize it by the thickness, so it's an energy sort of normalized by volume. And written in terms of the original map, it would involve the gradient of U. So in the new map, it involves this gradient H of Y, and that is now over a fixed domain. And this function W, of course, determines the specific elastic properties of the material you're considering, whether it's steel or aluminium or rubber. Each would give a different W. It simply measures what energy is needed to perform a certain affine deformation. So we don't need to know anything about the details, we just need some structural properties of W. And these are very simple. So the first one is that W should be invariant under rigid motions. So in other words, if I pre-multiply by a matrix in SON, the energy should not change. Then it's also convenient to normalize W so that its minimum is achieved at the identity, and by this invariance it's simultaneously achieved on SON. And then you want it to come out of the minimum in a non-degenerate way. So W of F should be bigger than constant times distance squared F from SON. Yeah, so this says that you have a quadratic minimum and not sort of a degenerate minimum. And last, sort of for some arguments, it's convenient to assume that W is twice differentiable, but you actually only need this, and really I'm working in 3 dimensions, that it's twice differentiable near SO3. So it could be very wild, far away. For example, you usually want to put it plus infinity on the matrices with negative determinant, because you don't want sort of to turn a right-handed body into a left-handed body with finite energy. So these will be our structural assumptions on W, and actually for this talk I will use a model which saves me sort of writing some constant, and the model will be simply that WF is actually simply the distance squared from SO3. Otherwise, the quadratic form given by the second derivative of this at the identity will come into the picture. So here it's particularly simple because it's totally isometric. So
what happens with real materials? To what extent is this?
with what materials?
With actual materials that you find in the world. Is this
Okay, so this is a so-called hyperelastic material, where the energy only depends on the deformation gradient, and sort of a very good model for this are, for example, rubbery materials. There you can do, say, a 200% stretch without any breaking or anything, and it's totally elastic, so when you let loose, it goes back to its old state. So real materials do other things. They break, for example, at a certain critical stress. That's not included here. Real material, like in particular metals, also do what they yield. Also plastic bags do this. If you pull them before they break, you can really feel that when you keep the stress constant, they start to flow. So that's also not included here. There's a poor man's version of yield, which is really sort of a dynamic or quasi-static phenomenon, sort of purely energy minimization, by making this grow linearly at infinity, because that means that the derivative sort of saturates, and so if you try to impose something which is larger, then it cannot really do that. So these are effects which are not included here. You could try to build more complicated theories where they are included. So the interesting thing is when you go to thin objects, then as already indicated here, the energy, even for large deformation, becomes very small. So at least in some L2 sense, your gradient is very close to SO3. If it was close to SO3 in an L infinity sense, then you would be sure that you're always in the elastic regime. So another answer to your question is that as long as this is sufficiently close to the identity or sufficiently close to SO3, almost all materials are well described by this. But when you go further away, then different behavior kicks in. So one advantage of nonlinear elasticity over linear elasticity is not only that it can sort of handle large strains like in rubber, even for small strains, this is in some sense much more satisfactory because it has the full invariance under rotations, whereas linear elasticity is only invariant under infinitesimal rotations, and that's in particular unsatisfactory for a situation like this, where clearly from here to here you have a big difference in rotation. Okay, so what we want to study is somehow the limit of these functionals as h goes to 0. And we're not interested in a pointwise limit, but in a so-called variational limit, so in a limit which will capture the behavior of minimizers. And there will be the notion of gamma convergence, and I'll talk about that later. But the first interesting result is that if this energy goes down with the thickness at a certain rate, then you already get a compactness result. So this is compactness. So suppose you have a sequence of deformations YH such that the energy is bounded like a constant times h squared. So if you like, if the functional divided by h squared remains finite. I'm not assuming anything else. In particular, they don't need to be minimizers or anything. It's just based on the energy. Then, and I say it once and I might forget to say it in the future, there exists a subsequence, which I don't relabel, with the following property. So first of all, modular constant, so let me put constant of h because the energy doesn't control translation, so I haven't put any boundary condition. This converges strongly to y in W12, so the gradients converge strongly in L2. So that's already a little surprise, because a priori from the energy you only have an L2 bound on the gradient, and that gives you weak convergence, but by no means strong convergence. So the new thing is if you control the energy with a specific scaling, you get strong convergence. Then another feature which is not surprising is that the third derivative becomes 0, but that essentially comes simply from the from the rescaling of the gradient. So 1 over h y comma 3 remains bounded, so no surprise that the limit will be independent of x3. But another surprising fact is that the limit gains one derivative. The limit has two derivatives in L2. And in fact, you can say a little bit more. What you're really interested in is not just the gradient, but what you're really interested in is this scaled gradient, because that's the real sort of elastic variable. That converges strongly to, of course, gradient prime. And also the scale component converges strongly in L2. And the limit map, then is no surprise, will take values in SO3. So this is not meant to say that it's a constant, but it takes values in SO3. So once you have strong convergence, this just follows from the behavior of the energy, of course. And a remark is that this is sharp in the sense EI, no compactness if you only have a bound with h to the beta for beta less than 2. So if you give me a beta, I find you a sequence which satisfies this and which is not compact. In fact, what it does, let me draw it in one dimension. So what it does, it would map sort of a thin strip into something wavy. And okay, actually, if you do this if you do this nearly isometrically, it would look like something like this. And then when you pass to the limit, and the limiting map would map this to a strip which is now shorter, because you lost some energies in making all these wiggles. And you can choose the period here going to 0 as long as you have anything weaker than h squared. But with h squared, this can no longer happen. Okay, so the second result actually derives the limiting theory, and I want to conserve the, well, I cannot conserve everything. And okay, as I said, I'll do that for this particular case, otherwise you have to write a quadratic form somewhere instead of the identity. So this will be in the sense of gamma convergence, and I'll explain that in a second. So now it's natural to rescale the functional by h squared, and then in the sense of gamma convergence, it converges to a limit, and the limit is can be expressed as an integral only over the surface, and it's nothing but the L2 norm of the second fundamental form. So I'll explain it, and there's a factor 112 in front. And this is for all admissible y, and plus infinity if y is not admissible. And what are the admissible y's? Well, strictly speaking, the y's sort of are functions in W22, and we can view them as function from the original domain into R3, but the first condition is in fact that they should not depend on the third variable, so I can alternatively view them as functions on S alone. And then the main condition is that they should be isometric immersions. So yi, y comma I, the derivative with respect to I, y comma j should be delta ij. So the and A is nothing but the second fundamental form, so it's minus yi second derivatives scalar product with a norm. So I should draw a picture. So the situation here is now that we have a surface here sitting in R2, and we have an isometric immersion Y, mapping this to something in R3. This has a normal nu here, and since it's an isometric immersion, nu is nothing but Y1 batch product Y2. And this theorem, of course, this limiting functional was, of course, not invented by us, but it appears in a beautiful paper by Kirchhoff in 1850, and it's actually in Kreller's journal, volume 40, if you want to look it up. So that's exactly Kirchhoff's theory, except that he assumed a priori that the limiting problem somehow would be defined only on isometric immersions of the midplane, and he assumed that this vector B, which you get here, which somehow says what happens in the sin direction, that this would have to be normal to this plane. And so if you like, what we did is we proved that the so-called Kirchhoff hypothesis actually are rigorous consequences of the energy, and then that once you have that, it's actually not difficult to derive this form of the functional. This more or less comes from a Taylor expansion. If the midplane is isometric, then the amount you differ, the induced metric differs from the identities exactly controlled by the curvature, and is roughly speaking linear in the third direction. So we have to do careful Taylor expansions, because in the whole process you never have L infinity bound, but you only have L2 bounds. But if you do that the right way, then you get the right form of the energy. Sometimes the harder part is sort of to get this compactness so that you really end up with isometries, and the example I showed you before showed that the scaling is critical for that. Okay, let me say at least very briefly what gamma convergence mean. So that goes back to the Georgi, and say very abstractly a sequence of functional on a, if you like, metrizable or second countable space, which can take value plus infinity. Gamma converges to some limit I, if and only if two things are satisfied. So on the one hand, you want for every sequence, say, xh converging to x in the topology of that space, that liminf IH xh is bigger than I of x, so that's some kind of joint lower semi-continuity, or and the second condition is that I is the biggest functional with that property. So there is, for every x, there exists sort of what we call a recovery sequence, such that you get equality here. Of course, you can write this with the lim sup, and then if the first condition holds, then this is equivalent to that. And so the meta theorem is that gamma convergence is the same as convergence of minimizers. Or since the original problem may not be lower semi-continuous, you may have to consider almost minimizers. Minimizing sequences which become closer and closer to the infimum. And what you need to make this an actual theorem is sort of some kind of equicorsivity to sort of get compactness in that space for energy-bounded sequences. And for this, you have to put a sufficiently weak topology on this. And you may be surprised that this could be equivalent, because here you only talk about minimizers, and here you talk saying something about all sequences. But the idea is that this notion is obviously stable under adding a continuous perturbation, continuous with respect to the topology here, And by adding a continuous perturbation, roughly speaking, you can at least make every point a minimizer of the limiting problem. So therefore, it should not be so surprising that the two things are nearly equivalent. Okay, so in whatever time is left, I want to say at least a few words about the proofs. And maybe I'll be very brief for the compactness result. And then instead I say a bit more about this geometric result. So proof, so compactness, I'll be very brief. So you have your plate here, and now it's sort of more convenient to draw it again in the original variables. Of course, you can transport all the calculations to the rescale. And so you divide it into cubes of size h, and on each of these cubes you can bound the gradient minus a constant, which depends on the cube you're considering, in L2 by the, let me just write Q times energy, if I can write W. And there's a certain constant here. And we know that this is very small. Assume now, say, it was even small in L infinity, not just in L2. And the main thing you now have to control is how this rotation changes from one cube to the next. So you do it for a Q prime here, so you get the same estimate for Q prime, but with a different rotation. But now you can apply the estimate also to the union of these two cubes. I didn't say, but it's clear that the estimates, of course, are invariant under just dilation. And by applying it to the union of these two cubes, you obviously get an estimate for the difference of these rotations in terms of the energy. And if you trace all the powers the right way, this gives you essentially a difference quotient estimate for these rotations. And in the limit, so this gives you compactness, and in the limit it also gives you one derivative more. And you can do this for the rotations, and then when you carefully, you can do that for V as well. And that is essentially done by sort of pushing powers around, and you have to be a bit careful near the boundary, because you can't translate the whole way, so you can only use tangential translation and so on.
How do you get this constant for your H squared?
Well, so here the constant is of order 1, of course, because I'm doing it for a cube of size h, but the constant is the same as for a cube of size 1, because the estimate was scaling invariant under dilation in all directions simultaneously. And of course, in the course of the proof, I use that when I sum this over all cubes, then here I have the total energy, and that's bounded by h squared. So when I say, and now I sort of translate, say by order h, then essentially I get this term twice, and I control by twice this. So when I translate by order h and I divide by h squared, I still have something bounded, and that's the difference quotient estimate I was mentioning. So let me very briefly then say something about the rigidity estimate itself. And sort of 50% of the proof can already be understood from the rigid case by giving a PDE proof, which actually goes back to Reshetniak. So let's consider as a warm-up, let's consider the case that the gradient is actually in SON, if you like, almost everywhere. Then we use two facts. If you form the cofactor matrix as a gradient of a gradient, yeah, so that's a matrix of n minus 1 by n minus 1 minus, and then you compute its divergence by rows, this is always 0 for a smooth map, and sort of by modification it's true for a Lipschitz map, for example. So that's one fact, and if you think in differential forms, that is really just the fact that dd equals 0. Because this cofactor you can sort of view as sort of pullback of a certain form. The other thing you uses this condition, namely this uses this cofactor f actually equals f when f is in SON. When you put these two things together, you get that V is harmonic, which immediately gives you that V is smooth. And now for harmonic functions, it's always a good idea to look at the Laplacian of the energy, and that is twice Laplacian of gradient V plus twice all second derivatives squared. Okay, but now we are done, because since V is harmonic, this is actually 0. Since V is in SON, this is a constant, namely n, so this is 0. So this says that the matrix of all second derivatives is 0, which is the same as saying that V is a constant. Now, being very brief, what's the idea in the perturbed case? So now we only know that distance gradient V SON is some function f, which is in L2, and we want the bound in terms of the L2 norm of f. Well, the first step imitates this, and there you get that V can be written as a W plus Z, where W is harmonic, and Z is controlled by divergence of f, and Z has 0 boundary conditions. So for Z, you get the L2 bound for the gradient right away. You only have to control the nice harmonic part. When you try to emulate this argument, you get a good estimate for the second derivative, but unfortunately it comes with the wrong power. So to cut a long story short, you get that the second derivative of W is bounded by a constant times f in L2, but only to the power 1/2. And then you need to do some extra work, the other 50% to finish. And there the main idea is, now that you know that it's harmonic, you also have a bound in high norms. So you know you're close to a single matrix on a small enough ball. And this matrix you can choose to be the identity, and then you can linearize near the identity, and then you can either reprove or use Korn's inequality. So I don't have time to do that in detail. And if you do that carefully, this argument first gives you an interior bound, so a bound on a smaller subset, and then there's a nice exhaustion argument by cubes going to the boundary, sort of the kind of usual Whitney argument. And when you sum all this estimate up carefully and you use the kind of Hardy estimate, then you finally get the full bound. But I think I've taken up enough of your precious time, and I'm happy to explain more in private. And I want to close the first lecture with this. Yes? No, I mean the three-dimensional form is standard, and the two-dimensional is due to Kirchhoff. This was exactly what he sort of proposed on slightly formal grounds in his paper. So essentially what he did is he assumed that the deformation is of the form that the midplane is, it's a deformation of the midplane plus some linear variation. And then you can check that the midplane, of course, must be deformed isometrically, and then you sort of arrive at this. But of course, a priori, it's not at all clear that the three-dimensional deformation will look like this. Maybe there's a more complicated way by sort of, say, taking a sheet of paper and sort of crumpling it in some complicated way, which has lower energy. So what we showed is that this is not the case in sort of this classical form you get. I didn't have time to say is you can also look now at other scalings. If the energy is even smaller, then you don't get something where the rotation makes a large change, like here, but the rotations actually all will be close to a single rotation, so you can do a further linearization, and this way you can, for example, derive the von Karman equations, which have been sort of, there have been lots of fights in continuum mechanics because the usual derivation almost sounds self-contradictory, because at one point you assume that something is very small, and then later it's not small, and
What inequality?
the von Karman equations. So they're a set of equations which are very popular in engineering applications, while sort of you have your plate here, and you deform it, and essentially you have an out-of-plane deformation, which is the dominant one, sort of it scales with h times v, and you have in-plane deformations which are smaller, they scale with h squared times u. And then the functional is a functional involving determinant. So that's not really incompressible. That's all. That says you can't revert the orientation.
But if you're bigger than one, or
yeah, the incompressible case is a bit more delicate, and I would have to think how to do that. So this we haven't tried. So the incompressible case violates this condition that V should be C2 near the identity, because in some directions, namely those where the volume changes, it jumps immediately to plus infinity. So this would require rethinking the argument. Of course, the lower bound and the compactness would work the same way, but you would have to reprove the upper bound. And this I would have to check what you get.